So in today's lesson, I want to talk to you about intramolecular forces, and then we'll move into reviewing molecular polarity. So you'll probably remember all of the concepts in this lesson from grade 11 chemistry. And if not, make sure you ask some questions. So to start off, when we talk about intramolecular forces, we're talking about forces that exist within a particular molecule with covalent bonds. So intra is a prefix that means within. So when we talk about intramolecular forces, these are those forces of attraction that exist within a molecule. So to juxtapose intra and intermolecular bonding, both of which we've covered in grade 11, we're talking about intramolecular forces, where we would be talking about in this water molecule the forces of attraction between, my hydrogen atom and my oxygen atom of a singular water molecule. Whereas if we're talking about intermolecular bonding, those would be the forces that exist between adjacent water molecules. So the hydrogen bonding is not an intramolecular force because we're not talking about the bond that exists between two atoms within a single molecule. So you'll probably remember, but it's still good to review, that we can identify the type of bond that exists between two atoms by just looking at electronegativity and electronegativity differences. Now, those are values that you can find on your periodic table. So let me just take a moment to locate that. So I'm going to just zoom in here on this periodic table, which should look pretty similar to the one that you have. And I'm noticing here that there's, electronegativity is right here. So just below the atomic number, there should be a value. So for instance, fluorine has an electronegativity of 4.0. Fluorine has an electronegativity of 3.0, and so on and so forth. So going back to our note, if we were to take a look at those differences, we would see that if two atoms in a particular bond had electronegativity differences between 0 and 0.4, and I'm going to talk more about this value in a second, then we would consider that covalent bond to be nonpolar. If I see that the difference between the electronegativities of the elements in that bond is between 0.4 and up to 2.0, some would argue that that's 1.7. If the electronegativity difference between the two atoms in that covalent bond or in a bond is huge, is greater than, usually it's 1.7, but this resource is saying 2.0, then we could qualify that as an ionic bond. And really what that means is that the other atom is so much better at attracting electrons that it actually would grab the electron away from the neighboring atom, forming ions. So now moving on, I wanted to just talk quickly about how bond type and the range of electronegativities that would give you a different value for, or a different maybe choice for which type of bond it is. You need to know that the quote unquote cutoff between nonpolar and polar, and even polar, covalent, and ionic differs from source to source. Some textbooks will say that at 0.2, suddenly a bond might be considered polar versus nonpolar. As we just saw on that previous page, 1.7 was exchanged for 2.0. I believe that these are the values that our textbook uses, and so we'll go with that. But please understand that really polarity, it's not like we have these boxes that molecules fit in and certain types of bonds fit in. It's a continuum. So we're more likely to talk about one bond being more or less polar than another bond than talking about its absolute polarity. So let's look at a couple of examples to help kind of practice identifying this skill. And so if I were asking you to identify the type of intramolecular forces present in a molecule of hydrogen cyanide. So hydrogen cyanide has the formula HCN. And so when we're drawing this out, we're going to first count up the number of electrons that are available. And so I've got 5 from my nitrogen, 4 from my carbon, and then 1 from my hydrogen. So I've got 10 electrons to work with in this structure. And so I'm going to put my carbon in the center because it has the highest bonding capacity. And then I'm going to put my nitrogen around and my hydrogen around as well. Now, hydrogen can only form a single bond. And I know that my carbon in this case, is not going to be satisfied, but I'm going to go through the procedure. And so I've used up 2, 4 out of my 10 electrons, 5, 6, 7, 8, 9, 10. But of course, the octet of my carbon is not complete. And so I'm going to move some electrons from my nitrogen into the bond. And that's going to give me a triple bond between carbon and nitrogen. So I'm just going to get rid of some of that business and just recreate my structure. So it should look like that. And so if I want to look at the electronegativity, the type of bond that I have between carbon and hydrogen, so carbon, I can very easily look up its electronegativity, and you should see that it's 2.5. And then hydrogen's electronegativity should be 2.1. And again, that's just looking at my periodic table and identifying those charges. And so that gives me an overall difference of 0.4. So, what would I say about this? Well, again, depending on the resource, I might call this nonpolar or very weakly polar. Okay, now I'm going to look at my carbon to nitrogen. And so nitrogen on my periodic table has an electronegativity of 3.0. So I have 3.0 for nitrogen, and then I have for carbon, I've got again the 2.5. So difference of 0.5. So both of these bonds, as it turns out, are fairly weakly polar. So carrying on, I want to talk now about determining the polarity of a molecule. So you'll remember last year that we started to talk about how it's possible for a molecule with polar bonds to be nonpolar. And that's because we need to look at the overall sum of the dipoles or the net dipole of the molecule. So I've found these 2 examples here. And if we were to examine our periodic table, we would see that, the bond between carbon and hydrogen is such that carbon with its higher electronegativity would be slightly negative. And conversely, our hydrogens would each be slightly positive. And that's again just, the value with the higher electronegativity is going to pull electrons closer to itself and thus have a partial negative charge, right? So carbon has an electronegativity of 2.5, hydrogen 2.1. So that allows us to create these vector dipoles from our positive, slightly positive pole towards our slightly negative pole as such. And remember that this is a 2-dimensional depiction of something that's actually 3-dimensional in nature. So I'm simplifying it in this way, but in 3 dimensions, each of these vectors that are symmetrical around our carbon atom in that tetrahedral configuration are all going to be equal but opposite and therefore cancel. So what I have in this first case is a non-polar molecule but with polar covalent bonds. They're weakly polar, having said that, but they're still polar. So now if I look at my second example, I have, the same situation here with my hydrogen and carbon. So I'm going to have vectors pointing towards my carbon from hydrogen, just as we just saw. But when I examine the distribution of electrons around carbon, between carbon and chlorine, carbon has a lower value of electronegativity compared to chlorine. So chlorine would be the slightly negative pole in that interaction, and carbon conversely is a slightly positive. So I would be drawing my dipole vector in the direction of chlorine. So in this case, the vectors are not of equal magnitude and they're not all pointing in directions such that they cancel. So the molecule on the right would have a net dipole and therefore be polar. Now, hopefully you remember that from last year, and that's a quick refresher, but please ask questions if you have any. So, just to reiterate, it's possible to have a polar covalent bond or multiple polar covalent bonds within a molecule, but the dipoles add up to give, and cancel out each other. And so there's a net zero dipole for the molecule, and that makes it nonpolar. Okay, so let's take a look at what I mean by this. So the dipole vector sum is one way to kind of think about whether a molecule that has polar bonds will also be a polar molecule. So I'm going to take the example of HCl, simple example. So I have HCl, and if I look at this molecule and the electronegativities, chlorine has a higher value for electronegativity. It will be my slightly negative end. Hydrogen is my slightly positive end. What that does is it creates a net dipole in the direction of my chlorine. And so this is most definitely a polar molecule. But if I had other atoms involved in this, if this molecule had more than 2 atoms, I would need to look at the net sum of them. Another way to look at molecular polarity is to examine symmetry, molecular symmetry, and so we're going to look at that also. But I have a kind of a list of like criteria using water as an example. So this is kind of my thought process for around like about how I would go about doing this. So I'm going to use water, like I said. So I'm going to just draw out a water molecule here. So here's my bent configuration. And again, now we're expecting you to understand VSEPR theory and how that helps to determine molecular geometry and electron arrangement. So the first thing you would want to do is identify all the dipoles, and we've been doing that, right? So I would say in this case, I've got a dipole in the direction of my oxygen because oxygen is slightly negative relative to hydrogen, right? So let me just put in those symbols for slightly negative, slightly positive, slightly positive. And so I've drawn in the directionality, and I can write out their magnitude if I want to. And so oxygen from the periodic table has 3.5 and hydrogen is 2.1, giving me a difference of 1.4. And so now, I'm going to say if there are no dipoles, then the molecule is nonpolar. That's not the case here. So for all molecules with more than 2 atoms, look at the combined effect of all polar bonds and by looking at the dipole sum. So I can tell right away here and that if I were to look at these dipoles, I would have a dipole in that direction, summing that with a dipole of equal magnitude in the opposite direction. And so my net dipole in this case for water would be up. Now you don't need to know the magnitude of it, but I would have a net dipole in the upward direction. So what that tells me is that if my dipole vectors do not cancel, the molecule is polar. That's what I'm seeing here. So I would say, therefore, this is a polar molecule. Okay, in some cases, the dipole vectors will cancel. Like we saw in that first example of CH4, that would mean I have a nonpolar molecule. Now, if vectors are a little bit confusing to you, another way to look at this is to look at symmetry. Okay, and this is particularly useful if we have 3D molecules. We're not going to start adding vectors in 3D. So basically, you're going to look at symmetry. Are the ligands symmetrical about that central atom? And are the dipoles, that would make our dipoles equal in magnitude, but the opposite direction, and then cancel. If I have an asymmetrical molecule, then that molecule is likely to be polar. So that's just kind of a reference for you to get a handle on how to identify polarity. Let's look at an example. So in this example, it says predict whether each of the following are likely to be polar or non-polar molecules. Okay, so the first thing that I would do is I would draw out a Lewis structure for this and include like the VSEPR distortions if there are any. And so chlorine has 21 available electrons in total, plus 5 from phosphorus. I'm working with 26 electrons. I've got my phosphorus in the middle and my chlorides all around. And so I'm going to use up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I've got 2 extra electrons there in my central atom. And so what I can see now is that this is definitely has a trigonal pyramidal kind of orientation. And so in this case, I need to think about that lone pair there as being like an electron cloud. And so this molecule should probably be polar because I'm seeing a lack of symmetry there. But let's just, because that ligand is missing. So when I look at the electronegativity difference between chlorine and phosphorus, however, let's take a look. So phosphorus is 2.1 and chlorine is 3.0. So I'm looking at a difference of 0.9. So in the direction of chlorine, those vectors are not going to cancel each other out. If this was trigonal planar, it would be symmetrical and they would cancel. But in this case, it's not, and so those vectors are not going to cancel. That means that in this case, I have a polar molecule with polar bonds, difference of 0.9 in each case. Okay, next. And if you want to pause the video to give this a try, and then we can take it up, then go ahead and do that. So when I look at SO3, I see that I have 4 times 6 or 24 electrons to work with. And so my structure is going to look like this. So I've got my O's all around. And I'm going to put bonds between each of my atoms. So with 24 electrons, my octets are all going to be full. And except sulfur is not happy. So I'm thinking I'm going to need to have an extra bond here. But I need to just take a minute and look at my orbital diagram for sulfur. So sulfur has electrons in the 1s, or sorry, the 3s rather, the 3p, and of course it has that empty d shell. And so, ground state, it would have an electron orbital diagram that looks like this. But I know it needs to make more than just 2 bonds because it's got 3 ligands. And so I'm going to suggest that we first of all take an electron from here in the 3p and move it into the 3d. And that allows, now I have 1, 2, 3, 4 bonds that were made, and so the structure looks like it's legitimate. Okay, and so now I'm looking at this and I'm seeing, well, there are no lone pairs on my central atom. This is a trigonal planar molecule. Now I need to say, well, but what are the bonds? What are do I have any dipole vectors here? So when I look at oxygen, it has an electronegativity of 3.5. Sulfur is 2.5. So there's definitely a difference there that's worth noting. And so I know that I'm going to have some dipole vectors, each of magnitude 1.0, around in the direction of my oxygen, slightly negative, slightly negative, slightly negative, and then my sulfur slightly positive. So those are not going to cancel, or those are going to cancel completely. So even though I have polar covalent bonds, my intramolecular force, my intermolecular, my molecular polarity is going to be non-polar because of that symmetry. And that means it's a non-polar molecule. Okay, and now one thing to mention that you may not have been sure about is VSEPR. When we're talking about VSEPR and molecular polarity, that double bond is counted sort of in the same way that we would a single bond, just for clarity's sake. Okay, one more example. Predict whether each of the following is likely to be polar or non-polar. I want you to draw that out and use your knowledge of VSEPR to help you, and then pause it when you're ready to take the question up. Okay, so I'm seeing here that I have four atoms, each with 7 valence electrons, so that gives me 28 electrons to work with. And so if I'm kind of doing an analysis VSEPR-wise, I know that with 3 ligands, each needing 8 electrons to complete their octet, I'm going to use up 24 electrons with my ligands. Now that gives me 28 minus 24. That gives me 4 electrons, which equals 2 lone pairs. So I'm dealing with 3 ligands, 2 lone pairs, which gives me a total of 5 electron clouds around that chlorine. And now remember, chlorine has an empty 3D shell, and so I can move electrons to make that happen. And so I'm going to have 1, 2, 3, 4, 5 electron clouds around that central atom, but I have 2 lone pairs, and so that means that I need to get rid of my ligands in the axial plane from my chlorine. So I'm going to give 1, 2, 3, 4 electrons there. And that gives me a T shape, finishing off my structure. And so I can see very clearly that this is asymmetrical, but are my bonds polar, right? And so chlorine has an electronegativity of 3.5 and fluorine 4.0. So I have my dipoles in the direction of my fluorines. Even though the magnitude's low, there's still going to be a net dipole, and so the correct conclusion here would be that this is a polar molecule. Okay, all right, I hope that that helps. I think that's the last example I have. No, I have one more example. All right, so let's take a look at this. If I were to say to you, in each pair, identify which you would predict to have a higher boiling point, H2S or H2O, and explain your decision. All right, so I want you to pause the video and give that one a try and see how you do. And when you're ready, resume the video. Okay, so I'm going to draw out the Lewis structure for each of these. Okay, and we know how to draw water. And so H2S is pretty similar in terms of how the electrons are arranged. So let's get that going. Okay, so first of all, when I look at the electronegativity difference between hydrogen and sulfur, sulfur is 2.5, hydrogen is 2.1. And so I have a dipole in the direction of my oxygen in the case of H2S, but that dipole is relatively small. In fact, some may argue that this is not as a non-polar bond, non-polar covalent bond. And so even though, we could say that there's a net dipole, that net dipole is going to be quite small. In the case of water, however, I'm looking at a much larger dipole. I believe it's 1.0 in the 1.4 rather in the direction of my oxygen. I'm going to double check that, having said that. Yeah, 3.5 and 2.1. And so my dipole in the direction of oxygen is going to be much larger. So now, when I look at higher boiling points, like what determines boiling point has to do with how much individual molecules are going to interact with other molecules of that substance. And so in the case of my H2S, that dipole is going to be pretty small. Whereas with water, it's going to be quite large. And so, what that's going to create is within the molecule of water, a slightly negative pole that is quite distinct from that slightly positive pole and quite stronger. And so that's going to attract adjacent water molecules towards it and thus make the boiling point harder to achieve and therefore higher. H2S with its small little teeny little dipole, net dipole, is not going to be as easily able to draw other H2S molecules towards it. therefore it's going to be easier to separate molecules of that substance, and therefore will have a lower boiling point. Okay, so which would have the higher boiling point? Water would have the higher boiling point. Hoping you did okay with that. In each pair, identify which would you, this is the same question, different molecules. So pause the video, give that a try, and then see how you do. Okay, so when I look at xenon tetrafluoride, I'm going to count up its electrons. So in total for xenon tetrafluoride, I've got 4 electrons from my fluorine, so that's 28 in total, plus 8, so that's going to give me 36 electrons to work with. So drawing out that structure, I'm going to have 4 ligands, each with let me just kind of work this out. So I've got 4 ligands, each needing 8 electrons. So that's going to give me 32 electrons that are used up. So that gives me 4 electrons left over, 4 electrons left over in my lone pairs, or 2 lone pairs. So I've got, in total, I've got 2 lone pairs plus 4 ligands, 6 electron clouds around my central atom. Okay, so I've got xenon with 1, 2, 3, 4, 5, 6. So I've got here an octahedral electron configuration. And when I have an electron configuration that's octahedral with 2 lone pairs, I'm going to get rid of my axial ligands and replace them with electron pairs. So here it looks like I have square planar. So square planar with 4 fluorides around. And if I fill those octets, for the interest of time, I'm not going to do that. But I can see that I have a symmetrical molecule, so this is symmetrical. So therefore, this is going to be nonpolar. Now let's look at SF4. So SF4 conversely, I've got 28 plus 6, so this is got a structure with 34 electrons. And so instead, I'm going to have 32 electrons, 32 electrons caught up with my ligands, but only 1 lone pair. So, I've got 4 ligands, 1 lone pair. In the case of SF4, sulfur tetrafluoride, my sulfur's in the middle, but I have only 1, 2, 3, 4, 5 electron clouds around it. And my 1 lone pair gets removed from the equatorial plane. So let's do that. Equatorial plane gone. And fluorines put in place. I can see very easily that this is asymmetrical. So it's asymmetrical and therefore polar. And I'm done. So which would have the higher boiling point? Definitely the one that is polar is going to have stronger forces of attraction between adjacent molecules and therefore be harder to separate, therefore higher boiling point. Okay. Hopefully you did okay with that harder example. It's a way that we kind of connected some of our previous understanding with more recent stuff. And that's the end of this video. So I'm going to assign you some homework associated with this video to work on in class tomorrow. If you're not in class tomorrow, then that will be on Google Classroom. Look for a second video on on intermolecular forces coming up.